In order to understand why 0.1 plus 0.2 does not equal 0.3, you need to understand numbers. And let's start with numbers that you and I understand and we've been brought up with, and that is in the base 10. And all this means is that there are 10 symbols that represent all quantities. And we know this, we've got 10 fingers. And this is probably why we've done it this way. So let's look at our 10 digits, our 10 symbols from 0 to 9. When we say 0, we just mean there's nothing. When we move one placement to the right, we know that that is 1. In this case, we get 1 warthog. If we move 1 to the right, we know that represents 2 warthogs. And so forth and so on. When we get to 5, we know it's 5 warthogs. When we get to 9, we know they're 9 warthogs. But what do we do now? We've run out of digits. Well, now we just repeat the process, but we separate out the tens versus the single digits. So we've got a 1. We've gone through the iteration one whole time, and now we start at 0 again. And that gives us our solution of 10 warthogs, represented by the symbol 1 and a 0. You and I know it as 10. And you can represent this in an entirely different way. Let's take the number 32 for an example. We know in base 10 we've got symbols that represent each digit. And as I mentioned before, once you go through one iteration, you move along. So the 3 we can put in the tens bracket, and the 2 we can put in the singles bracket. And because we're working with base 10, you can represent this as 10 to the power of 1 times 3 and 10 to the power of 0 times 2. Quick side note, anything to the power of 0 is equal to 1, not 0. So this is known as the long format. But you're probably thinking computers don't work in base 10 format. We know computers only work in binary. So let's take our 10 digits, our symbols, and let's break it down just to 2, because this is all a computer works in, a 0 and a 1. And now let's start the process again. How do we represent nothing? Well, that's the same as our base 10, it's just 0. How do we represent 1 warthog? Well, that's also the same, it's just the number 1. But now what do we do? Because now we've run out of digits, we've run out of symbols. Well, we do the same process. We start a new iteration. So to get to 2 warthogs, it's represented by the numbers 1 and 0. What about 3 warthogs? Well, let's keep going along. A 1 and a 1. Can you see now we've run out of digits again? No problem. We start a new iteration. 1, 0, 0 will give us 4 warthogs. And you can literally keep going with this process to get to higher and higher numbers. So to recap, in binary, a 0 is represented by a 0 and a 1 is represented by a 1. But 2 is already represented by a 1 and a 0, because we need to scale up. Just like in decimals, we did that after the number 9. And if we continue, 3 in binary is 11, 4 is 100, and 5 is represented by 101, and so on. And this brings us all the way back to our question. Why does 0.1 plus 0.2 not equal 0.3 in binary? This isn't just a JavaScript problem. This happens in other languages as well. To find out why, let's just recap a little bit. Remember how we said the ECMAScript standard only recognizes one number type in JavaScript, and that is the double precision 64-bit binary format? What does this all mean in this context? Well, let's take another step back. In maths, 0.1 is a rational number. And all I mean by a rational number is that it's the result of a ratio between 2 numbers, a 1 and a 10. We have no issue with this because maths is typically base 10. So going 1 divided by 10 is doable in maths, and we know that's represented by 0.1. And we can easily calculate numbers like 0.2, which is also 2 divided by 10. But what happens with irrational numbers? Irrational numbers are numbers that can't be written with a finite series of digits. We cannot measure 1/3 in base 10. What is 1/3? Well, it's 0.33333, and it just continues on forever. And think about that. We actually cannot represent this number in base 10. Weird, right? But now, remember how I said ECMAScript only recognizes one number, double precision 64-bit binary value? Well, when you break that down, it uses different amounts of bits to store different pieces of information. Remember in the previous lecture, we saw how you had the significand, you had the mantissa, the exponential, and the base. Well, to cut a long story short, the reddish bits you see on the screen is what stores your actual number, and it uses 52 bits to store that number. And in base 10, we just took 1 and divided it by our base, which is 10. But with computers, we only have base 2. So the first iteration we can do is only divide it by 2. And with 64-bit, this means we can only keep halving 53 times. And to represent this in a way that I think will make the penny drop, and you go, I get it. Imagine we had this pizza, and we could only halve this pizza 53 times. This is binary. And this is the smallest amount of a slither we can actually get in binary. It's the highest level of precision. Now, once you've halved this 53 times, that slither is going to be tiny, right? But let me ask you this. Can you take a certain amount of those slithers and add them up to get 1/10 exactly? How about 1/5? Answer is you cannot do it. It won't give you the exact right answer. Let's look at the number 0.1. If you added up all those slithers, immediately less than 0.1 is the number 0.09999999916733332, etc., etc. That's what you see on the screen. And if you added one more slither, you're going to get a number that's slightly more than 1. And the difference between these two numbers is literally the smallest slice that you have to decide whether to include, which introduces an upward bias, or exclude, which introduces a downward bias. The JavaScript parser will prefer the higher number as it's closer to 0.1. And this process is exactly the same for 0.2. And what does this mean for us? Well, it means the result is an approximation of 0.1 and 0.2, and both of them are scaled upwards. And this is why 0.1 and 0.2 is slightly higher than what we would expect. And you know what's interesting? If you didn't take the higher number of both of those, if the parser didn't do that and you took the lower of the two, you would actually get a much closer number to the true answer, which is 0.2999999997769, etc., etc. But the parser doesn't act that way. The interpreter does scale them both up, and that's why we get 0.300004. I hope this makes sense. To me, this was really a aha moment when I came across it. I think it's interesting, and I hope it helps you understand numbers in JavaScript in more detail. This is really awesome stuff. Let's keep going.